In this video we're going to discuss section 2.4, which talks about the inverse of a matrix. So just as motivation, the n by n matrix, which we denote I, fulfills the role that the real number does for multiplication of real numbers. That is, just as a times 1 is equal to 1 times a is equal to a for any real number a, so AI is equal to IA, which is equal to A for any n by n matrix A, right? So in other words, the identity matrix behaves exactly the way uh, it behaves exactly the same way the number 1 behaves for multiplication of real numbers. And in real numbers, every non-zero real number that you pick has a multiplicative inverse. That is to say, if you pick, for example, 2, you've got half, such that 2 times half becomes 1, right? However, in matrix multiplication, as we have seen in example 2.2.21, that this is not true, that every matrix that is not a zero matrix is a multiplicative inverses. And this example, we had a non-zero matrix that did not have a multiplicative inverse. And so this section is devoted to those matrices with multiplicative inverses, and these are the ones that are called invertible matrices, right? So let's start off with the definition. Definition 2.4.1 in the textbook. Let A be an n by n matrix. If there exists an n by n matrix B such that AB is equal to BA is equal to the identity matrix, then we call A invertible and B is called the inverse of A. And in this case, we write B to be equal to A to the power minus 1. And we can say A inverse is equal to B. Right, so, and then a remark is, if A is invertible, then A inverse is equal to B. And if A is invertible with A inverse equal to B, then B will also be invertible, and B inverse will be equal to A, right? And this just comes from the definition. So here we said AB is equal to BA is equal to I, and then concluded that A was inverse. So just by also looking at this, you can see that BA is equal to AB, which is equal to I. So that means B is invertible, and its inverse is A, right? So note that matrix multiplication is not commutative in general, and this we did show in the previous section that this is not true in general. But however, in this special case where inverses, when we are dealing with a matrix that is an inverse, you'll see that these two special matrices commute. So this is theorem 2.4.3, which will show us that. So let A and B be n by n matrices. Then the following statements are equivalent. AB is equal to I, BA is equal to I, and the third one, A is invertible A, and A inverse is equal to B, right? So what this theorem tells us is, if you look at the definition tells us that for us to see that A is invertible, we have to find a B such that AB is equal to BA is equal to I. But what this is saying is, if you know that AB is equal to I, it also automatically means that BA is equal to I. That's what it means to say these statements are equivalent. And so, and Therefore, that means A will be invertible. So what it's saying is, if you want to check if a matrix is invertible, you only need to check if you can find a B such that AB is equal to I, and that is sufficient. That's what the theorem is saying. Now let's look at the proof. So for the proof, if you look at 3, you will see that from the definition, if A is invertible, then AB is equal to I and BA is equal to I. So 3 implies 1 and 2. And if you also look at the definition here, you will see that if I take these two, 1 and 2, they will imply 3. So if 1 and 2 are true, they imply 3. So what is left to show is the fact that 1 implies 2, or 2 implies 1, whichever. It's the same thing, right? And the proof of that part is a special case uh, that is left as an exercise. That's exercise 2.4, number 5 in the textbook. So the proof, it's not the full proof, it's just a proof of a special case that is going to be considered in that. So as I've mentioned, using theorem 2.4.3, to show that a square matrix A is invertible, it is sufficient to find a matrix B such that AB is equal to I. You don't have to show that BA is equal to I also, right? And then let's look at some properties of inverses. And this is theorem 2.4.4 in the textbook, and it says, let A and B be n by n matrices. Then the following statements are true. So if A is invertible, then A has exactly one inverse. So the inverse of a matrix is unique. And then number 2, if A and B are invertible, then the product of A and B, AB, is invertible, and its inverse is B inverse A inverse. And in this case, you need to note the order of matrices, the order of the product, this inverse. It's B inverse A inverse when it's AB. Remember that matrix multiplication is not commutative, so the order really matters, right? So if we wanted to find the inverse of BA, we would say A inverse B inverse, right? In this case, we have got AB, so we say the last matrix first, its inverse first, times the other one, the first one, the inverse of the first one, right? So this order really matters. And the proof again is an exercise, exercise 2.4, and that's numbers 3 and 4 for both statements. Right. Now, what we want is to be able to find an algorithm or a way of finding an inverse, right? How we now know that if we can find a matrix B such that AB is equal to I, then we have found the inverse of A. But how can we do that? So we are going to spend most of this video trying to establish, or rather most of this section trying to establish how we can find a way to get an inverse of a matrix. So let A be equal to Aij and B be equal to Bij, be n by n matrices. Denote the rows of A by, so the rows of A, we are going to think of them as vectors. So A1, A2 vector, AN. So this will be row 1, row 2, up to row n. And the columns of B by column 1, we call it B1, column 2, we call it B2, column n, we call it Bn, right? And so what we are just saying is AI. So if we are given any any raw vector AI, we know that what we are talking about is AI1, AI2, up to AIN. And if you are given any column vector Bj, we are going to have B1j, B2j, up to Bnj. So that will be the column vector that we have. Right. So, so in this notation, we write the matrices A and B as, so because we have rows in this case for A, the A's are the rows, the B's are the columns. So we will have row 1, row 2, up to row n. And for the case of B, we have column 1, column 2, up to column n. Right. So we can write our matrix in that form. Right. So if we look at these two examples, we can see that A1 becomes A1. A1 becomes the vector 1, 3, minus 2. A2 becomes 2, 0, 4. A3 becomes 0, 7, 3, 1. And if we think of B1, that will be minus 2, 3, 2. And B2, 1, minus 1, 2. And B3, 0, 2, minus 5. Those vectors, right? Okay, so we have a theorem of how to multiply matrices. So AB, let A and B be n by matrices given by A is written in that form, B is written in that form. Then AB, so the matrix AB is going to be equal to, so remember when we put this, we are saying the ijth entry of that matrix. So the ijth entry of AB is going to be the dot product of the row vector AI and the column vector BJ. Right? And this can also be written as this. So if you think of the notation that we have just introduced, so if you think of B, if you look at B here, you will see that this is the first column. So AB1 will be the first column of AB. AB2 will be the second column of AB. Up to ABN will be the nth column of AB. And the proof is left as an exercise 2.4, number 6 in the textbook. Right. Let's look at some equivalent statements of saying that A is invertible. So now we know what it means for a matrix to be invertible. Now we want to find, in terms of um, systems of equations that we have been working with, what does that mean? So let A be an n by n matrix. Then the following statements are equivalent. Number 1, A is invertible. Right. Number 2, the only solution of the equation AX is equal to the 0 vector in Rn is x is equal to the 0 vector. So the only solution of this equation is the trivial solution, which is, by trivial solution, it's x, which is that a column of which is just a column of zeros, right? And then number 3, the equation AX is equal to B has a unique solution in Rn for any B that you pick. So if you have AX and you put any B there, as long as A is invertible, you're going to get a unique solution, right? So that's what it means for A to be invertible. So in other words, for example, if you were to say, okay, how can I check if if A is invertible? You can just create a system where AX is equal to 0. If the only solution you get there is the trivial solution, is the 0 vector, then it means A is invertible. That's what the statement is saying. So let's see how to prove this statement. So 1 implies 2. So we are assuming that A is invertible, and we want to show that If that is the case, then the only solution for this system will be x is equal to the zero vector. So, so assume 1 is true. In other words, A is invertible. It follows from theorem 2.2.16, part 7, that x is equal to the zero vector is a solution of the equation ax is equal to 0. So remember that this theorem, the part 7, talks about A times the zero matrix being equal to the zero matrix. So in this case, the zero matrix is so what it's saying is A times the zero matrix. So in this case, it's a column vector. So A times this column vector will be equal to the zero vector in that case, because this part 7 talks about A times the zero matrix is equal to the zero matrix, but the matrix that we are talking about is just a column vector in this case. So in other words, x is equal to 0 is a solution indeed from this theorem. Now suppose we've got an arbitrary solution to this system, right? So we are supposing that we've got this C that is a solution to this system. So in other words, we can say AC is equal to 0. What we want to show is if C is a solution, then C has to be equal to the 0 vector, right? So using that theorem 2.6.16, part 6, part 1, and part 7, we know that C can be written as IC. So we can put the identity matrix there, and but the identity matrix can be written as A inverse A, and in this case, because we know that A is invertible, we know that A inverse exists, right? So we can write it as that, and then we use the fact that matrix multiplication is associative to have A inverse times AC. But we know AC is equal to the zero vector from that, right? And so therefore we have A inverse times the zero vector. And then again, part 7 of this theorem tells us that A inverse times a zero matrix will give us a zero matrix, right? And so therefore, in other words, C is equal to the zero vector. And so therefore, the only solution that we have for AX is equal to the zero vector is X is equal to the zero vector, as we expected. Right, let's get on to the next implication. So suppose 2 is true, and we want to show that if 2 is true, then 3 will also be true. So assume that 2 is true and let B be a vector in Rn. So we want to show that Ax is equal to B will have a unique solution, right? So according to theorems 2.3.6 and 2.3.15, if you look at this system A0 vector, it is going to be row equivalent to a matrix C0 vector. So we are using what we know already. We are using this fact that the only solution here is this. So we created Ax is equal to 0. We know that it's going to be row equivalent to some matrix C0, where C is in echelon form. And for this to be for this to be the only solution, it means that the diagonal entries in that matrix, in this matrix C, have to be non-zero. For all the diagonal elements, they have to be non-zero. Now, so we know that, so if this happens, we know that AB is going to be row equivalent to CD, with D a column vector in Rn. So basically what we are saying is whenever you reduce a system to echelon form, whatever you put on this side doesn't really matter in terms of the matrix A, right? So you're going to still get the same row echelon form. We know that the row echelon form is not unique, but what I'm saying is if A can be reduced to C, whatever is on this side will have to follow the row operations that were done, but otherwise the A and the C will still be the A will still be reduced to C using the same row operations, right? What we just change is the B and the D, whatever we put on the right hand side, but whatever happened on A and C will be the same. So in other words, the system AB is row equivalent to system CD, where D is some vector in Rn, right? Now since CII, since every diagonal entry is not zero, it follows from from theorem 2.3.15 that Cx is equal to D has a unique solution, right? But AB is row equivalent to CD. So by theorem 2.3.6, the equation Cx is equal to D and Ax is equal to B have exactly the same solutions because they are row equivalent. So if they have the same solutions, what it means is the 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 equation Ax is equal to B has a unique solution. Right, let's look at the last part of this theorem. So we are assuming that 3 is true, and we want to show that if 3 is true, then 1 is also true. So in other words, if this has a unique solution for any B that you pick, then A has to be invertible, right? So assume 3 is true, and then denote E1, E2 up to En to be the columns of I. Then for each J, so for each column, the equation Ax is equal to Ej has a unique solution, and we are going to call that unique solution Bj. So we are creating this system. Ax is equal to Ej, and we know from 3 that it has to be a unique solution. So if we call that unique solution Bj in Rn, then it means that B is equal to, so this is supposed to be B1, B2 up to Bn, right? So that is supposed to be B1, B2 up to Bn. Then by theorem 2.4.6, we had a notation, a way of writing AB. We said AB will be equal to A times B1 as the first column, A times B2 of being the second column, and A times Bn being the last column. But remember that we said Bj is a solution to this system. So in other words, if I say AB1, it is going to be equal to E1. If I say AB2, is going to be equal to E2. So in other words, we have AB1 E1, AB2 equal to E2, and ABN equal to EN, and that is just I because we had assumed that these are the columns of I. So therefore AB is equal to I, and we know that if that is the case, that is sufficient for us to conclude that A is invertible, and this is by theorem 2.4.3, and that the inverse is B. The inverse of A is B. Hence, 1 is true as we wanted. So, thank you. We'll continue with this in the next video.